Okay, testing from Boston. Hi everyone. Hi Leon, hi Simon. Yeah, I hope that the audio is okay. Hi Churong. Great. Fingers crossed. Hopefully the internet connection stays stable like this throughout the lecture today and tomorrow. Good. Yeah, it's time. Let's go ahead and start. Okay, you can hear the air conditioning. Well, it's probably a bunch of other electronics I have nearby the laptop's microphone. Well, I hope that it's nonetheless bearable, the background noise. All right, and yeah, hi Jiaxu. Okay, good. Okay, good. All right. Polly is speaking from Boston, and let's see how this will work. Okay. So first thing first, the to-dos this week. Sorry about flashing, because Polly does have a lot smaller screen space to play with. So I'm actually using the virtual desktop and stuff. And so as I turn from one desktop to another desktop, you might see a little bit of flashing here there. I'll try to keep that minimal. So first, so there's no Google Meet session today, but there will be a Google Meet session tomorrow because the quiz tomorrow, quiz 26, it's one of the most important quizzes and one of the most fun quizzes that is gonna give you a good idea of how congestion control is done in TCP. And it's a very special quiz as well. Those who complete the first phase, it's a competition actually between the teams. So definitely make sure that you and your teammates are attending the lecture tomorrow. So you guys will compete for phase one. The winner gets 5 points, extra point for class participation, and that's on top of all the YouTube or Slack or email or office hour participation. Okay, so entering first, passing phase one gives you that. If you finally win a big prize, that's 20 points extra. Okay, so it can probably make up for like four weeks of 4 weeks of participation. So quiz 26, it's big. And it's fun. So make sure that you attend. And for the quiz 26, there's going to be a Google Meet session. In order for you to compete in the second phase to win that 20 points, you do need to call in from Google Meet. Okay, and Polly and you will be interacting. Okay, and see if you manage to get things right. All right, so that is the first thing. Second, yeah, just like every week, we do have a few assignments doing. This week, the PA assignment is PA number 7. Now, number 7 is quite different from the past PAs. Previously, we work on building sockets and sending files, receiving files. Now, we are actually trying to interact with the web server or generating code that might work like somewhat like a client. Okay, so PA7 is to make sure that you learn the web server part of coding already embedded in Golang. Okay, it's very, very nice and convenient. So make sure that you know how to exploit that part of Golang. Okay, and again for PA7, much like the earlier PAs, you might want to go through the companion videos. Okay, for PA7, that usually will make it easier for you to work on PA7. Okay, I do notice that some of you kind of skip those videos and try to work on things on your own based on previous students' programs. Okay, you see that the trouble working this way or learning this way is that you are always backward engineering what the question was. And so you pay less attention to what the questions are or what the problems are. So when you see a real problem, you had trouble understanding what the problems are, or you are a little bit careless about what the problems are saying. So you do want to learn how to backward engineer. That's actually a good skill, but you also want to learn how you go the other direction. Okay, read the question, see if you understand the question, and you try to think for a solution, and then you communicate what your solution is. So this is the other way of solving problem, and most of us in real life solve problem this way. Okay, so PA7, it's going to be a bit unusual. Now we also have 4 quizzes that you need to submit by Saturday. Okay, so today it's going to be just quiz 25. So some of these quizzes are very open this week, but some are more for you to exercise the mechanisms, okay, specific mechanisms we talk about. And yeah, sorry guys, exam 2 is coming up next week. If you click into channel exam 2, you will see, hey, the day, next Thursday, the time, yeah, look very similar to exam 1. The scope is tentatively PA 4 to 7. Okay. Also, in terms of lecture, the scope is chapter 2.6, multimedia networking, all the way to the end of chapter 3. We'll see. We might not be able to finish everything in chapter 3, but by the end of next Wednesday's lecture, you will know exactly the scope of exam 2. Other than the scope and the date and time, all the rest, the set of rules, the process, you'll be using Google Form, you need to join a Google Meet session, those will all remain the same. Okay, so to make sure that you don't screw up for exam 2, make sure that you go back to the exam 1 channel and read through the rules, okay, and read through what the process is going to be like. Okay, good. And similarly, bullet 4 and bullet 5 here are just to let you know that the Google Form link will eventually be here, and the Google Meet link will eventually be here as well. Okay, now something that Polly wants to add a little bit more for exam 2 is this. As you have already experienced exam 1, you see that it's very, very long. And that is the first time you take an exam like that. But you see, if you think about it, it's a little bit more like real life, right? That you have a long to-do list, you have many more things you need to do than the time you have. So the exams is realistic in a way. You have more to do than the time you have. So how do you address or handle a situation like this? So you do want to sit down and pay attention to the set of things you need to do, right? And you want to prioritize them, okay? And you might want to focus on the problem sets that have more points to earn, or you might want to focus on the problem sets that you have better understanding, a better handle of, okay? So you see, there's a PDF file that Polly uploads right after Polly said the exam begins. So you can definitely exploit that PDF file so that you can skim through all the problem sets quickly and learn the point distributions. Okay, and so you could have like a plan of which problem you want to go first and which one the second. And so when you are working on some of these problem sets, you want to also recall every now and then that so this might not be as straightforward as you thought previously. And also, if you're observing exam 1, what Polly did very often is that for each problem set, there are more basic questions, okay, so the sub-problems. So you definitely don't want to skip those basic, straightforward problems in a big problem set. Okay, so maybe a better strategy is, of course, you plan a flow of the problem sets you want to work on. And within each problem set, if you start working to some point that you find, this is no longer straightforward, and you can quickly skim through into the rest of the sub-problems. If you are not really comfortable spending more time struggling with them, you might want to switch to another problem set and work on the basic sub-problems there, so that you make sure that you earn all these, easy to earn points. Okay, good. Now, Polly didn't do this for exam 1 because Polly know that it's probably hard for you to imagine how it's going to be like. Now you guys all have experience with exam 1, and I know that many of you already know. Yeah, you want to quickly go through what are the problems and find out the point allocations, and so that you make sure you allocate time on the points that you know you will earn for sure. Okay. Something to also stress is this. I do observe that many of you know that the exam is going to be long. Therefore, you try to be very quick. But you see, it's also fair. When you try to be quick solving a problem set, you earn some time so that you can solve all the problems. But you see, that is a little bit tricky, isn't it? Because you try to be quick in one problem set, but you ended up skipping some of the descriptions. And those descriptions might be critical for you to earn the points, you see. So again, similar to real life. If you rush, there's also a risk. Okay, so you want to be calm and steady, and kind of stay afar and don't get too emotional when you are working on the exams. And so if you run into a problem that is a little bit challenging for you, maybe switch to another problem set and work on the easier ones. Okay, and maybe take a note on the side. Okay, which are the problems that just need more time, but you are able to solve next. Okay, and then there might be problem sets that you find, okay, this is probably far off. Okay, it's okay. It's okay to skip those. Okay, because chances high that other students will also have to skip those. Okay, all right. So try if you can learn how to cope with this anxiety or emotion you have when you're taking a test, when things get hard, and that's no longer that straightforward. All right, so that's about the exams. And now, topics for today. We have 2 more topics we are yet to talk about regarding TCP connection. First is flow control, the other is connection management. Okay, so let's start from flow control first. Oh, wait. And that takes us to the flow control of TCP. Allow me to explain. Okay, so this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. Okay. If everything is okay, TCP receiver is going to extract data and pass it further up. Okay. What's going on really in the implementation in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, okay, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Okay. Just like the TCP receiver here is going to push more data into the receiver buffer. Okay. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more, because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So flow control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined, and it's actually the size of the receive buffer space. Okay. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher. All right, so that's full control. You see the goal there is just to make sure that the receiver buffer is not exhausted and you ended up having packet drops, right, at the receiver. And you don't want to have packet drops entirely. So the next topic we'll talk about is congestion control, and that is to avoid packet being dropped inside the network. But of course, then equally important, right? You don't want packets being dropped at either end, sender or receiver. So that is the goal of flow control. And it's quite straightforward. You just track the free space and you inform the sender, hey, there's more free space, you can send more, or no, there's not much, right? Slow down. So set the window size a little bit smaller. Now, connection management. So this is about establishing the TCP connection at the first place, and then you might do reliable data transfer, trying to get data through. And also in the end, when you're done with transfer, you also do this, disconnect. Okay, so connection management is about establishing the connection and removing the connection. Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay? At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay? So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, that needs to be initialized. Okay. And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seq num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose an initial sequence number to tell the receiving of the request messages. And it's gonna be sent in a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags, one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere. And that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now, the server will then in the sync received state. So server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. Okay, so sync ACK is such a packet. That is to ACK receiving the sync packet. The server here will be doing yet another thing, choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. And in sequence number, server tells the client it's going to start from Y. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is X plus 1. All right, so next seek num is already set to X plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. So it's just an ACK packet, and the ACK number is Y plus 1. Because this guy here observing the initial sequence number of the server is Y, then therefore the next seek num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close, and ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Then it's going to enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Server here receiving the fin packet sends back an ACK. So ACK bit on, and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Some more ACKs waiting to come back here. So server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin. It's pretty much done, and just waiting for the server to say everything is already sent, so you're okay. So finally, server says, done with all the data. So sending fin. Client here is receiving the fin, sends back the ACK. Saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection? All right. Okay, good. So quick recap. You see that in connection management, we send special packets, right? Sync packet, and there might be ACK for the sync packet. We send a fin packet to close the connection, and there are ACKs for these fin packet as well. What's a little bit unusual here is this. Those ACK packets, or those sync packets, those fin packets, they are just control. What's important is that flag in the header being turned on, the sync bit or the fin bit. So there's no data at all in the payload. But then the ACK packets of the sync or fin packet will always increment the sequence number by 1. All right. So it's I don't know exactly why, but TCP just does this. If it's a sync packet, even though there's no data, the ACK packet of the sync packet will be sequence number of the packet plus 1. All right. I guess that's a way to avoid the first control message and the second control message. In case they are both sync packets, then you will have trouble, right? Knowing exactly which is which. All right, so because sync packet can be lost and retransmitted, for example. All right, and we do have 2 questions, and so let's answer those questions before moving on to a new chapter, okay, or a new subchapter. So the first question is from Anna. We won't be covering anything in exam 1 for exam 2. So you can forget about things that you're tested in exam 1. All right. Kevin, how does a client or a server decide what is the initial sequence number? Yeah, so I think the X is the sender side of data, and Y is the receiver side of the data, right? So there's a pair of X, Y for this direction, and then there's a pair of X, Y for the returning direction. Okay, so how does the 2 ends decide the initial X and initial Y? That's a very good question. I guess it's definitely not in the TCP protocol documentation, but there are probably some common practice one can imagine. So if using the same port number and the previous connection using the port number is using the sequence number to some point, let's say A. If that connection was already closed, but a new connection needs to be started using the same port number, I would say if I'm a programmer, I would choose an X that is A plus something that's big enough so that I won't be mistaken a packet that got stuck in the network from the previous connection to arrive and I thought that, hey, this is a good data for me. Okay, so usually I can imagine that the X is chosen such that it was the previous sequence number, okay, plus some number. Okay, so I hope that addressed the question. Oh, we talk about quiz 24 today. Good question, agent. Good question, agent. I did not plan to do that, but I'll definitely attend to quiz 24 a little bit more. Okay, your solutions is actually perfect, by the way, agent. Yeah, so in case you're still not quite sure about what the real solution for quiz 24 is, let me know. Okay, there's sometimes a quiz being that there's just no one solution, and it's probably more that as long as you can justify for your answer, then it's okay. All right, so I think we had a quiz like that last week. I think that is about which side, client or server, uses more memory in go backend versus selective repeat? And many of you are actually correct, but some of you say that you use more memory for the sender side, and some of you say that you think it's more at the client side, or at the receiver side. But they are actually all okay. It really depends on how you justify your answer. But for quiz 24, it's actually there's a solution. Okay. All right. So okay, Kevin, glad that I addressed the questions you have, and Caffrey had a follow-up question about the ACK sequence numbers. Is it possible the ACK num plus 1 because received ni no longer than same base? ACK num received needs to be larger than same base. I mean, the ACK numbers are very often the same base, which is okay. I mean, wait. I'm a little bit confused. Well, you know what, Caffrey? I think that's a very interesting question. It confuses me. Okay, so let me hold on to answer these questions a little bit later. And how about we go on with the lecture and start talking about congestion control? All right. So here's the overview video. Principles of congestion control. Now, the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion, you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. Right? So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now, when we're talking about network congestion, congestion is occurring here, routers. And these are the machines that are in the core of the internet. And the resources that we are exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now, when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packet waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing. All right, so 3 scenarios. The first one is the simplest, but it's the least realistic one. So Caffrey, I would try to, let's hold on to answer your question after the lecture because I'm running out of time really. So let's go through these videos at least. Okay, so first scenario, simplest. Scenario 1 is this. Okay, you see here, we have 2 senders, host A and host B, 2 receivers. Okay, so 2 servers receiving requests, I suppose. So 2 senders, 2 receivers. And we do have a link in the middle. And the capacity is what? R. And there's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops. because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are two flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate. All right, so that is already very unrealistic. Assuming you have infinite buffer space, you still see a weakness or a disadvantage of sending too much traffic into the network. Really long delay. Now the second scenario, let's be a little bit more realistic. We have only finite amount of buffer space. And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have what? Packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer process is generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in because it should definitely contain the amount of data we need to send out and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay, and that goes back and we remove the copy. Right, so this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing, and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the center side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remained the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into an already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case. Right. So you see that long delay, retransmission, these are we expect, but unnecessary retransmission. Yeah, when congestion happens, this is actually unnecessary retransmission happens a lot. And the last scenario, which is the most complex, but the most realistic. If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning, but saturates toward the end, okay? So beyond certain point, the more work you do, you don't get more results. Okay? But here, I'm gonna show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. Okay. And each of them is generating a flow traveling multiple hops. So this is one hop. This is the second hop for the red flow. Okay. So multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops. and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Okay. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing and sometimes increasing faster than lambda in. Now, what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. Okay. And as the lambda in increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Red packet will be dropped, but blue packet will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, the more output we get. But as it approaches half of R, we see blue flows, blue packets gets dropped a lot. So originally, not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, okay, than when the lambda in here is small, okay? Really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay, it's all wasted. Okay? The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So, so congestion is bad. All right. So we have only 3 minutes remaining. So I'm cutting my video a little bit shorter, okay, because the final conclusion is simply congestion is bad. So all these 3 scenarios, they sounded a little bit complex, and there are many strong assumptions. So Kevin was asking, why is lambda R divided by 2? In the ideal case, that is in fact also assuming that the 2 senders will get equal share. Okay, and I guess that's why Qiandi and Belang ask the subsequent questions. No, we're not talking about Shannon's theory here. It's just a few cases to illustrate such that you get a better sense. Congestion is super bad. All right. I hope that you get it. And we do have a quiz we need to at least show today. Okay, so that is quiz 25. But similar to the quiz 24, 23, that we don't have time to walk through them all as you solve them during the class. But what Polly will do is to go back to quiz 23, 24, and maybe 25 to let you know whether you get a hang of it or not. And here's quiz 25. All right. So this is a quiz that's a little bit similar to the Lord of the Ring quiz. Okay, so we have not yet talked about congestion control and how TCP does congestion control. But you see, congestion control is something that we run into every day. Okay, without knowing TCP solution, without knowing other people's solution, you might have a good handle of addressing a problem like this. Okay, so this time in quiz 25, I ask you to role play a Uber driver. So pretend that you're an Uber driver and you transport customers from Taipei City to airport and back frequently. And so this picture you see is highway number 1 connecting Taipei to Taoyuan, Taichung, the other cities in Taiwan. Okay, and you see that on Highway 1, as you take a customer to the airport, it's badly congested. Okay, so Q1 asks, what are the reasons you see congestion on the freeway? All right, so Q1 is very important. When you know what the reasons are, then you know better how to answer Q2. Okay, so when you see congestion, you would really try to avoid congestion, but you are already stuck on the highway, right? How can you try to alleviate, the situation? So one thing is, of course, you can try to tell your friends who are also Uber drivers, so that they don't get on the highway. So you might get stuck in between Taipei and maybe the new Taipei. And so you definitely want your friends who are also driving customers don't get on from New Taipei to Taoyuan segment. Okay, so you want to avoid further traffic coming into highway number 1. So you want to inform your friends to not get on. Okay, how do you do that? How do you inform your friends? Okay, you're already in the middle of a congestion. All right, good. So Q1, Q2. What are the reasons of congestions? Q2, how do you inform your fellow drivers? And so they can avoid taking the route, of course, and so that the congestion gets a chance to resolve. Okay, so now go to Slack. Okay, let me post the quiz. And you know what? It's all the time we have already today. So what Polly will do is to go over your solutions after the lecture, maybe on Saturday. Okay, but this is just for you to exercise. You can potentially come up with solutions on your own for problems that we have already experienced of. Okay, good. And guys, that's all the time we have. And I would suggest Kathy to stay a little bit longer, or in case you are curious, because there was a question from Kathy about ag +1 for the ag of sin and fin, the sequence number being the x +1. Why? So Kathy was saying that, so let me see if I can find Kathy's question. Yeah, so he was asking, is it possible we add the sequence number by 1 in the ag, because the ag sequence number should be larger than sem base. You see that so the meaning of the ag number is to tell the sender what is the next sequence number expected. That is already the same base, or whatever the packet at the same base, the ending bytes of +1. Okay, so if you just send the sequence number, if there's no payload, it's already telling the sender what is the next sequence number expected, next byte expected. Okay, so in the ag packets, the sequence number is always the sequence number plus the payload size. And if the payload is 0, then it's just the sequence number. So it is still odd. The ag for sin, the ag for fin. Take the sequence number of the ag packet, the sequence number of fin packet. Even though the payload, there's no data. 0 bytes, it's still at 1. Okay, so it's odd. Yeah, but as I try to explain, this is probably because the sync packet has a sequence number, right? The fin packet has a sequence number. I think particularly for SYN packet, if that works and it's starting sending a data, that data sequence number will be the same as the sync packet, right? So it can be a little bit confusing. Yeah, so I think that's why the ACK of the sync packet, the ACK of the fin packet, these control packets where the payload is 0, we add 1 just to avoid confusion of the real data packet it's going to send next, okay, to these control messages. All right, good. Kathy, I hope that addressed the confusion. I think some of the students in the class might have a similar confusion. Okay, so that ACK number is always what the receiver is expecting next. Okay, it's definitely gonna be larger, but SYN base is actually the base of the packet ongoing. Okay, the ACK packet is already larger than the SYN base. That's what I'm trying to say here, if you think about it. All right. Okay, good. So, hey guys, run to the next lecture. I'll see you tomorrow morning. We will have quiz 26 happening the first hour. You don't want to miss the chance to earn big extra points. All right. Trying to establish a connection. Okay, good. So that's all. Bye, guys. Okay. Guys, go. Okay, bye. Yeah, it's a little bit odd. So just remember, the ACK sequence number is already larger than SYN base. It is already what the receiver is expecting. And the way we came up with the ACK sequence number, the data sequence number plus the payload is already doing that. And you see that in sync packet, the sequence number, and we are sending 0, right? So the ACK number is exactly the sync packet sequence number. That should still work. But you see the next data, the next packet, which might be the data packet, then will carry the same sequence number. And then you have the sync packet and the data packet carrying the same sequence number, right? Do you buffer the ACK packet? Do you buffer the sync packet and the data packet at the same time? Yeah, I mean, if you get an ACK packet with the sync sequence number, do you release the memory space to buffer the ACK packet? Buffer the sync packet. Yeah. So you do want to separate the sync packet from the subsequent data packets you'll be generating. Okay, bye. Bye. Go. All right. All right, good. Bye. Yeah, I guess some of you are still working on the quiz. You see, this is an open-ended quiz. Yeah, all of you should do fine here. Okay, as long as you come up with a reason, as long as you come up with a solution, telling the ways you can inform other friends, telling the ways to try to avoid congestion. or relief condition. Interesting. Yeah, so my screen is a little bit screwed up. Why? But this was okay. Ah, I see. Okay, good. Okay, everyone goes to work. Tell the exact location. Very good. Call. Oh, okay. So call the radio station, and the radio station can actually announce where the traffics are. Okay, interesting. Commute time. Accident. Oh, okay. So maybe you tell the car fleet company that you join, and maybe there's some system broadcasting to everyone. Interesting. Yeah, so the reason having conditions about the scene. Yeah, call your friends. Interesting. Okay. Very interesting, Vincent. Yeah, cars do drive in different speed, right? If we all drive in constant speed, then we should be able to move on. Yeah, it's always because there are some car driving slower than the cars behind. Use the radio or Uber app to inform them? Sure. Share the traffic image from satellite. Yeah, okay, so I think this is a good point. And if one opens up Google Map, you probably see traffic congestion, bad weather, accidents, vacation. Yeah. Okay, message over the app. Slack. Okay. Yeah, simply call them. 3 reasons. Okay. Vacation time. Super slow car. Okay. Exactly. Car have. Okay. And this is a natural or a very reasonable reason that cars slow down. Switching lanes. Okay, or coming to an exchange point. Have line, or okay, Facebook or IG, or call a radio station. Very good. Car crash. Bad weather. Yeah, so some sort of out of band communication, right? You are stuck on the freeway. You can't drive to your friends to tell them. So try to tell another way. Try to tell the situation another way. Okay, so Zhenggen was saying, just don't say anything because they also have Google Map. They can look it up. Interesting. Oh, Anna. Oh, wow. This is a very extensive set of reasons. Car accident, construction, lane closure. Yeah, sometimes you see this as the police are trying to do some sort of traffic control. Animal crossing. Okay, animal crossing, definitely. Bad weather. Potholes. Yeah. So really bad road conditions. Bad infrastructure. Interesting. Interesting. I guess it has something to do with the design of the highway, right? So, for example, a sudden turn that cars need to slow down significantly to get through safely. So, for a highway, you probably want to avoid like major, okay, large degree turns. Call them, share info on the app. Yeah. Yeah, so I think this is a good collections of what people have mentioned, other teams have mentioned. Great, good. All right, so with that done, I say I end the stream.